Welcome everyone to today's webinar, Ensuring Process Stability, Reliable Anaerobic Performance and Testing Protocols. My name is TJ Willits with Veolia Water Technologies, and I'll be your moderator for today's educational event. Just some housekeeping notes to go through before we get started to the technical portion of the presentation. You should obviously be hearing me speak now. If you're having issues with your audio, there's two ways to listen to today's presentation. That's using your headphones or your computer speakers. The other option, if you're having an issue with your computer audio, is to go ahead and toggle over and switch to the phone call method where you could dial in and listen via like a conference line. I just want to let everyone know that your microphone is automatically muted. However, we wanted to make it as interactive as possible. So we reserved some time at the end of today's presentation to have some Q&A. So if you have some questions related to the topic that we're discussing, or you have some other topic related to these anaerobic reactors, feel free to just submit those questions in the question panel on the right side of your screen. And we'll try to get to as many of those questions as possible. I'm not sure if everyone has attended all of our various webinars related to this subject, but we do post after the webinars online. You can go and access them at our website and watch all of those webinars at your own time on demand. And you can visit our website at veoliawatertech.com and click the on demand webinar button. And if you're looking for a webinar participation certificate to prove that you've attended this webinar, those that attend the live broadcast will be automatically sent their PDF participation certificate 1 or 2 days after the webinar. Also, I know there's some facilities that have are playing this webinar, say in a conference room. Since it's an automatic send out of the certificate, if you do have some other operators or colleagues or managers that need a certificate, you'll see in the survey after the webinar to go ahead and type their name in, and we'll make sure to make a certificate for them so they're accounted for. Okay, our next item of business is to introduce our speaker. You probably have met her or heard of her before on a previous webinar, but we're pleased to announce that Jill Jordan will be joining us for today's technical presentation. So at this time, I'm going to hand the webinar over to Jill. Jill.
Hi, everyone. Thanks, TJ. Let's go and start with that first slide. Agenda. A couple of things we're going to talk about today. Key elements to process stability, and that's going to, creating a healthy environment for your biomass, which is all important. Without the health of the biomass, your anaerobic system's not going to work. And anaerobic system testing protocols, what testings are important and what the test results should be in a typical reactor so that you have a stable and healthy anaerobic bacteria biomass in your reactor. And then at the end, as TJ said, we'll do questions and answers. Please write your questions in there in that chat box so we can go over them at the end. Questions are the best way to get your ideas or get your questions answered, obviously. But as you go along, if you have a question as we go along, please let us know. Okay, so let's start with the key elements to process stability. So there's a few things that are, that are most important to an anaerobic process, and that one of them is to recognize that the methane formation is the rate limiting step in most anaerobic applications. Not all of them. In the high rate systems like our UASB and EGSB systems, that is definitely true. In a low rate system that's doing solids digestion, that may not be true. The hydrolysis step in those reactors may be the rate limiting step. So we really want to keep in all of the anaerobic processes, whether it's high rate or low rate, is to keep the production rate of volatile fatty acids at or below the consumption rate of VFA. If you have volatile fatty acids at the end of your process, you're not completing the anaerobic digestion. So low effluent VFA typically indicates a healthy anaerobic system. So the other thing that's important to the biomass is that there's certain environmental, if you want to call them that, parameters that you need to keep track of, and that is the food. These bacteria need food, they need nutrients, they need a climate-controlled home, and they don't want any toxins in their environment. Hey, that's the same thing I like in my house and what keeps me alive. You can't live on sugar alone, so you need those nutrients. The food, let's talk about the food first. The food is the influent COD that's going into your anaerobic reactor. And it's that COD, the chemical oxygen demand, that's reduced in the reactor that forms the methane. And the food is typically, in our business, is wastewater from the food and beverage industry. So that's why you see a lot of pictures of food on this slide. The food waste out of the food industry production facilities contains COD. So that's what's going to be fed into your anaerobic reactor and what's going to be converted into methane. Nutrients. What nutrients? Why do we need nutrients? Well, as I just said, you can't live on sugar alone. So you need nutrients to grow proteins and grow biomass. So there's two types of nutrients. There's macronutrients and there's micronutrients. Now the macronutrients are obviously the nutrients required in the highest quantities, and they are nitrogen and phosphorus. And you need nitrogen and phosphorus because you need those to make proteins. And if you don't make proteins, you don't grow new biomass. And if you don't grow new biomass, eventually you won't have any sludge in your system and the process won't work. So how do we know how much nitrogen and phosphorus is required? Well, first of all, we know that you need, let's say 850 to 1250 to 5-to-1 ratio of COD to N to P in the influent wastewater to ensure that you have enough nutrients. And where did that ratio come from? Well, it comes from the fact that in the bacteria, nitrogen is typically 8 to 10% of that biomass, and phosphorus is about 2 to 2.5% in the biomass. So that's where those ratios come from. So the micronutrients are needed in smaller quantities, and these are mostly metals, and they're similar to our need for daily vitamins, if you will. The micronutrients that are needed they're sort of like, I'll call them mid-range macronutrients, are sulfur, sodium, potassium, calcium, magnesium, iron, and you need those. Again, because you can't grow proteins without sulfur, you need iron. These are all important to the metabolism of the biomass. And you need those in the range of like 5 to 15 milligrams per liter of influent. And the truly micronutrients are minerals that are needed in less than 1 part per million. You need aluminum, copper, cobalt, manganese, molybdenum, nickel, and zinc. Those are the big ones. And the big ones that are especially required and necessary for the methane forming bacteria are nickel, cobalt, and molybdenum. Now, you don't have to have these every day, all right? But it's best to have that. I mean, it's like you should take your 1-a-day vitamin every day. And that's what it's like for these micronutrients. You want to make sure they have them every day. If you don't have them every day, if you miss a day, no big deal. But if you miss feeding the reactor these nutrients for several weeks, eventually the biomass activity is going to drop and performance of your system is going to drop. So you don't want to, you want to make sure you're getting these nutrients to them every day. That's the bottom line. Okay, make sure that they're getting them every day, then you don't have to worry about them. And what's a climate-controlled home for these bacteria? The climate-controlled home refers to the fact that the bacteria work best in a climate where the pH and the temperature are controlled. Okay, so the pH is controlled in such a way that if the pH in the reactor is too low, our systems automatically add caustic or magnesium hydroxide or potassium hydroxide, something like that, to the system so that the pH is more in the neutral range. Okay, TJ. We didn't talk about temperature. Same thing for temperature. We keep the temperature by in an optimal range, which is like, body temperature. Okay, toxins and inhibitors. Substances that, if digested by the bacteria, make them ill or kill them. If it makes, my rule of thumb is, if it makes you sick, it's going to make the bacteria sick. And the obvious things that are going to make bacteria sick are sanitizers, bactericides, quaternary ammonia compounds, PAA is para-acetic acid, chlorine, oil, peroxide, lubricants, the list is there. And mainly, they're oxidizing agents. So you don't want to have any of those in. The big thing now I want to bring to everybody's attention is a lot of food production facilities are using quaternary ammonia compounds and PAA in their CIP processes. And they're using them because they're really, really good at killing bacteria. The quaternary ammonia compounds are especially a problem because they're especially extremely toxic to anaerobic bacteria. I mean, it only takes, less than a part per million for it to kill a lot of anaerobic bacteria. And the reason people are using these is because they're so good and they're very hard to neutralize, so they keep on killing. The PAA is also bad, but not as bad as the quaternary ammonia compounds. It's more easy. PAA is easier to neutralize than the quaternary ammonia compounds. But notice a lot of the things on these lists. This list is they're oxidizing agents. So we can put in monitors for ORP, oxidation reduction potential, which can alert us to the fact that some of these compounds are in the wastewater. And there are companies out there now that say that they have chemical compounds that will neutralize quaternary ammonia compounds and PAA. Some of them I've heard work quite well. The issue with me is in using these is that it's hard to tell how much of them to use. Unless you run it off the ORP measurement and adjust the concentration that way, it's awfully hard to tell how much you need to do that neutralization and allow to kill the toxicity, if you will. The other thing we need to be aware of is that things that are normally really good for the bacteria that you need to use sometimes or all the time, you need to add ammonia for nitrogen addition. The bacteria can only use nitrogen in the form of ammonia. But if you have way too much of it, you could kill the biomass. And when I say way too much, I'm talking about like 1,000 parts per million. So there's no way in a regular food production facility that you would have 1,000 parts per million of ammonia in the effluent, unless there was a refrigeration unit in the facility that was using ammonia for refrigeration and that had a leak or something. You need to add caustic a lot of times to adjust the pH in the reactors. But if you have too much, if you have a caustic spill, if you're using caustic in your CIP and you have a spill or you use a lot of it, you could cause the pH in the reactor to be much higher than is allowable or good for the bacteria. So too much of a good thing can be bad too. You have to be aware of that. Another thing to remember is that the bacteria inside your reactor that are doing your work, that are doing this COD reduction and cleaning your wastewater, they're naturally occurring. They're not genetically engineered. Each reactor at each plant, even if you go to a brewery to brewery, brewery A and brewery B are going to have slightly different bacteria populations in them. Each system develops, grows the population of bacteria that is specific to that wastewater, its food sources, and how the system is operated. That is, what do you keep the pH at? What's the temperature? How much nutrients are in there? And how much food does it receive? What's the how much food to bacteria are in there? Those all define and help determine what the genetic and bacterial populations that develop are in any given reactor. Next. Okay, so we learned what the bacteria need to live. Okay, but how do we tell if they're working good? We need to test them. Why are we testing? Because the bacteria can't talk to us. They can't tell us if they're feeling good or bad. I mean, you could just put bacteria in a tank and feed water into it and walk away, but you would never know if it's doing anything unless you did some testing. So you need to look at what goes into the reactor and what comes out of the reactor. And you need to also look at how well the not only what's going in, but what's coming out, but how active is the bacteria, so we can do activity testing. You need to know those 5 things. How are they, what's a measure of these 5 things? How much food is going in? What's the pH of the system? What's the temperature? Are the nutrients okay? And are there toxins in the wastewater? You need to test those to make sure that everything's in the good operating range for the bacteria. Very, very important. So what are we going to test? Okay, inline measurements and readings in our systems are going to be temperature, pH, sometimes ORP. I'm seeing us use ORP a lot more now, just mainly because those quaternary ammonias and PAA are being used so often. It's the only way we know whether they're coming down, so that's another inline measurement. The liquid flows, the biogas flows, the biogas quality, and chemical use. We can also keep track of the sludge addition and removal volumes. What testing do we do in-house? And we do these in-house because they're easy to do, and they're important parameters to know to determine if the system's working well. So we're going to measure the volatile fatty acids and the alkalinity. Typically, that test is done in one test. It's a titration test. If you don't do it titration-wise, Hawk has the ability to do them, or you can use a GC for the VFA. You need to know the total and soluble chemical oxygen demands, the total suspended solids, volatile suspended solids, settlable solids, the nitrogens, TK and ammonia, phosphoruses, and sulfates. Outside analysis, things that you don't want to do in-house because they're a pain in the neck to do usually, or usually it's a very expensive equipment to do it, are the BOD. BOD is a pain in the neck test to do, and the answers aren't always reliable, so send them out for somebody else to do. Micronutrients, you need to usually, to measure them in the range that we need, you usually need something like an atomic absorption unit, which nobody wants to be purchasing for a wastewater treatment plant. So again, send those out to be done. So where are we going to test these parameters? Let's just look at our high rate systems, which is there's 2 basic designs that Veolia uses. In the upper left-hand corner, you have I'll call it our old original design, where the influent went into an EQ conditioning tank, and from the EQ conditioning tank, the reactor was fed. The reactor effluent split and went to the sewer or to aerobic polishing, and some of it went back some of that effluent went back to the equalization conditioning tank as recycle. We kept the level in the equalization conditioning tank at a set point. So as the influent changed, the recycle volume would change because your reactor feed flow was constant. So the influent was what in that case goes into the EQ. The effluent, you can take off the effluent line or the recycle line. It's the same water. Typically, we would physically take the sample out of the recycle line, but it's still the effluent. In our new basic flow diagram, we have raw wastewater that goes into an equalization tank, a gigantic equalization tank with a pretty long hydraulic retention time. And from the EQ tank, we go into a rapid mix tank, which typically has a hydraulic retention time of less than a half an hour, so maybe 20 minutes or so. From the rapid mix tank, we have a constant feed rate into the reactor. And here again, the effluent from the reactor splits and either goes on to the sewer or further treatment and or recycle back to the rapid mix tank. Because here again, we're maintaining the level in the rapid mix tank. So the difference between the reactor feed flow and the influent flow is the recycle flow. And again, it's the same water. Recycle and effluent are the same water. So we would physically likely to take our sample from the recycle line because you're always going to have that line. If you stop the influent in either of these cases, the first case or the second case, if you stop the influent, you would still have water circulating around from the rapid mix tank or EQ conditioning tank to the reactor and back again. So those are the 2 basic high rate type systems where you would take your influent sample from, in the second case, from between the EQ tank and the rapid mix tank, and the reactor effluent is either the recycle or the effluent. In lower rate systems, some of you may have some lower rate continuously stirred tank reactors or lagoons, you would have the raw wastewater maybe go into an EQ tank, and from the EQ tank into a reactor, which is a CSTR, continuously stirred tank reactor. And you may have or may not have some sort of solids removal on the effluent, which is that lower diagonal membrane or centrifuge step. In this case, you would take your influent between the EQ tank and the reactor. The effluent sample in this case could be taken from a number of different places. If you didn't have the membrane or centrifuge on there, your effluent would be that effluent mixed liquor suspended solids combination sample, and that would be your effluent sample. If you have some sort of solid separation, either a membrane or centrifuge, for example, your effluent would either be the permeate off of the membrane, or the centrifuge, it would be the centrate. And then you would have sludge coming off the other end. But your effluent would either be permeate or effluent, and your influent would be from your EQ tank into your reactor. Okay, TJ. So where and how often are you going to do this testing? The pH, and these refer to those drawings that we just went over. The pH, you want to measure the raw wastewater pH, the influent pH, the reactor feed pH, and the effluent/permeate pH if you have a low rate system. And you would do that daily. pH is in line and so important to anaerobic digestion and to the activity of the biomass. The problem is pH meters go out of calibration a lot. And you're using at least one or two of these pH readings to control the pH in the reactor. So you want to make sure that the pH that it's using to adjust, the pH meter that's being used to adjust the pH in the reactor is reading correctly. What we typically do is, if at each pH meter that's in line daily, we collect a sample and bring it to the lab and check it against the lab meter, which we know has been calibrated every day. And if the difference is too great between what's the inline reading is compared to what we have in the lab, we'll take that probe out of the line, clean it, check it, and if necessary, calibrate it, and then put it back in. It's so important. Temperature, raw wastewater, influent, reactor feed, effluent. Very rarely do I have a problem, or have I seen a problem with a thermocouple or a temperature transmitter in any reactor. So they're pretty steady. But you need to know what it is, especially if you're controlling the temperature. Because remember, we want to keep the temperature and the pH and to make that climate controlled home best for the biomass. Oxidation reduction potential, already touched on that. You want to measure that in the influent or the reactor feed. Anaerobic digesters have a very low negative ORP. The higher the ORP, the positive ORP means that it's not good for anaerobic digestion. So if we measure the ORP in the influent and the reactor feed, and it's greater than, let's say, like -100 or -150, we know that there's too much oxidizing agents in the wastewater and it could be harmful to the bacteria. So that's why we want to measure it in the influents, because if we see that in the influent and the reactor feed, then we know we could have a problem and we want to take actions to correct that. The liquid flows are measured in line. You want to measure the raw influent flow, the influent flow, the reactor feed flow, the effluent flow, and/or permeate flow. Biogas flow, you want to measure that. You need to know how much gas you're making, because you're going to relate that back to how much COD was reduced. The biogas quality, you also need to do that calculation, so you want to measure that daily. Some of the Andrus Hauser now has a new, I guess, well, it's new to us, relatively speaking, gas flow meter that not only measures the gas flow, but also measures the methane quality in the biogas. I really like those. Also want to take care to measure the chemical use. If you don't care, believe me, the bean counters do, and you should care too. You want to monitor that daily. For instance, let's say that those micronutrients, you're only feeding a very little bit of that every day. So you want to make sure that it's really pumping. So you want to measure the drop of level in that micronutrient jump. So if you're not seeing it, that something's wrong, and maybe that pump has stopped pumping, or it's got airlock or something like that. And it could go on for days and you wouldn't notice it. So you want to be careful that you really do monitor that, so you know that you're really feeding the chemicals you think you are. You also want to keep track of the amount of sludge that you're putting in and removing, so you can do a solids balance across the reactor and calculate out how much biomass growth you have. Okay, continuing on about testing where and when. So those that we just talked about, except for the pH, are all inline measurements. All right. Now, these are the tests that you're going to do in your lab at your wastewater treatment plant that I suggest that you do at the lab in your wastewater treatment plant. Volatile fatty acids and alkalinity on the influent and the effluent and/or permeate. Okay, and you want to do that at least daily, especially on the volatile fatty acids of the effluent. Again, the volatile fatty acids in the effluent are going to tell you if the methane formers are keeping up with the acid formers. If I have volatile fatty acids in the effluent, it means that the methane formers aren't keeping up and you're not completing your anaerobic digestion process. So you need to do that at least once a day. If for some reason you see the effluent VFA is higher than you want it to be or it has been normally, that gives you a clue that something wrong and you want to go look to see what it is that you need to correct to get it back down. The total and soluble chemical oxygen demands on the influent and effluent, definitely every day. We're doing them on the total and the soluble for two reasons, especially on our high rate systems. Our high rate systems, the UASB, EGSB systems, are designed to treat soluble COD, but there's always solids in there. As much as as much as it says wastewater and not wastewater and solids, solids are always in that wastewater. So we need to know what contribution they're paying to the production of biogas, and if they are harming the system by not breaking down and washing out. So that's partially told to us by the difference in the total and soluble COD differences. Back to the solids, you want to measure the total suspended solids and the volatile suspended solids. Again, especially important for those high rate systems because you don't want solids in there. And if they do go in, we need to know whether they're volatile or inert. The settlable solids. On the influent, it's just going to tell you, it's just a visual to tell you what the solids look like going in. On the effluent, on high rate systems, it's very important because you don't want to lose the granular sludge that's so important to the high rate systems. So we want to make sure that we don't have a loss of granules, and the easiest way is to see that in settlable solids. On the total nitrogen, total ketyl nitrogen, ammonia, total phosphate, orthophosphate, and sulfate, again, these are all nutrients, or the sulfate could be a toxin. So you want to do those 1 or 2 times a week to make sure that everything's in the proper range for optimal range for operations of your anaerobic reactor. And you're just going to do those on the composite influent and effluent samples. Okay. So outside labs, I already discussed, you don't want to do BOD in-house, it's a pain in the neck, but you do want to check it against the influent and the effluent, and you really do that as permitting is required. The BOD is important here again because in the United States, your permit is usually written on BOD and TSS. So you need to know what the BOD is. Over time, you should be, if you test the BOD regularly of the influent and the effluent, you should be able to get a relationship between the BOD and COD and use that as an estimating what the BOD is. But I have to tell you, in Europe, they use COD and TSS and not BOD. And COD, as you know, is much easier and much more reliable test than the BOD, but we're still stuck with BOD here. The micronutrients you're going to do on the influent, the effluent, and the biomass about a couple times a year just to make sure that you have what you need. Okay? Okay, so now we know we're going to do all these tests. So what are the answers are that we're looking for to make sure that the bacteria are working well? Okay, so on the influent, we're going to measure, the VFA test. On the influent, the answer could be variable, but it should be monitored to determine the amount of acidification. And in the old days, when I first started in anaerobic digestion, we didn't really care about pre-acidification, but we're finding out that it's actually a pretty important thing. And we'd like to see about 15 to 30% acidification measured in the water, in the influent water coming out of an EQ tank up in front of the anaerobic digestion process. So we just find out again that it's important, and we'd like to see 15 to 30% in the influent to ensure good granulation. In the anaerobic effluent, the most important test, I think it's the most important test that you do on a daily basis to determine how well the system's working or not. You want the anaerobic effluent VFA to be less than 5 milliequivalents per liter, which is the same thing as 300 milligrams of acetic acid per liter. The closer to zero, the better. Okay. The closer to, if you have zero VFA, it means that the methane formers have eaten all of the acids that the acid formers have produced, and you can't do better than that. It's kept up. There's nothing more for the methane formers to eat. The whole anaerobic digestion process is complete. If you have up to 5 milliequivalents per liter, okay, but maybe we could try to do better. You might have VFA between 5 and 10 if you're like just starting up and you overload the system a bit. I wouldn't panic, but you need to keep an eye on it and make sure that it does come down eventually. If the VFA in the effluent's greater than 10 milliequivalents per liter, it could be inhibitory to the anaerobic methane formers, and so you want to make sure and look around to see what's causing the issue and get it corrected. Okay. Alkalinity. On the influent, it's usually close to zero, except when the processing facility is using a lot of caustic for CIP or in some part of the production process. But usually it's zero. On the effluents, we want the alkalinity to be greater than 20 milliequivalents per liter, which is the same as 1,000 parts per million of bicarbonate per liter. And why do I even care about the alkalinity? Well, remember the alkalinity is the ability of the wastewater to buffer out changes in pH. So the higher the alkalinity is, it's an insurance policy. Let's say you start to see a high VFA. Well, if you have a high VFA, that means I'm making acids, and acids are going to lower the pH. And we know that low pH is bad for the anaerobic biomass, especially the methane formers. So I have one problem with a high VFA, and I'm going to have another problem, which is a low pH, unless I have some alkalinity there to neutralize those acids until I can figure out what the problem is. So I want to have an effluent VFA of greater than 20 milliequivalents per liter to help with that buffer capacity. Okay. pH and temperature are inline measurements, but let's talk about them. The influent pH and temperature are going to vary all over the place. In the effluent, the optimal pH is 6.8 to 7.2. Actually, the optimal is 7.2, so I'm going to say the optimal is like 6.8 to 7.4. I don't want to see less than 6.8 in the inline effluent pH because it just gets too tricky, and why do I want to run and take a chance on screwing up my bacteria? And you can see from this chart on the left, that's the methane activity versus pH, and you can see that the activity is 100% at 7.2. If I go down to about 6.5, even if I go down to 6.5 pH, I'm down to 40% or so biomass activity. Well, that's not very good. I want the activity of my biomass to be as high as it can be to ensure that I have really good digestion performance. If I go up to 8, I'm down to 50% activity. And on the temperature side, which is the chart on the right, the maximum activity is at 37 C, which is about 98 or so Fahrenheit. If I go down to a a temperature of 25 C or 75 Fahrenheit, I'm down to 50% activity. And you notice on this chart that on the high side, the activity drops off very, very rapidly as the temperature increases. And you'll actually kill the bacteria if you get to a temperature of above about 40 to 42 degrees Celsius, which is 100, 104 degrees Fahrenheit. So you want to be careful with that. So that's why we control those two, pH and temperature. Thanks, TJ, we're good. So what are the influent and effluents, COD and BOD? Now, they can vary all over the place, but the type of reactor that you want to use for the digestion or the digestion of COD varies depending on what the COD and BOD is. In continuously stirred tank reactors or lagoons, the COD can be above 20,000 and usually is much above 20,000 milligrams per liter. On the high rate UASB and EGSB systems, it has to be and typically is less than 25 milligrams per liter. And why is that? That's because you want the hydraulic retention time of the influent in the reactor, not the digester feed flow, but the influent flow in the reactor to be less than 48 hours. Where'd that 48 hours come from? To be honest with you, I don't know. We just know from experience that if the HRT is greater than 48 hours, you're not going to get granulation. And if you don't get granulation in the UASB and EGSB reactors, that bacteria is not going to stay in there. And if you don't have bacteria in your reactor, it's not going to work. Now, the COD to BOD ratios can vary, and it's going to vary depending on the type of wastewater you have. As a rule of thumb, in the food industry, food and beverage industry, that ratio is 1.6 COD to BOD. For other industries, chemical, pulp and paper, it can be anywhere from 1.6 to 3.0, depending on what the composition is of the wastewater. Okay. Solids. What do we want them to be? On the influent, for the CSTRs, we don't really care. Anaerobic MBRs, don't care very much. In lagoons, we don't care very much. But on the UASB, EGSB high rate systems, preferably the TSS should not be more than 10% of the total COD concentration. And in the EGSBs, we really like it to be less than 500, but very rarely do we see that. But what does that 10% mean? That means if your COD is 10,000 milligrams per liter, that you don't want your TSS to be more than 1,000 milligrams per liter. Okay. On the effluent, on the low rate systems, CSTRs, lagoons, it's just going to be what your mixed liquor is, and that's going to depend on what your TSS is and what your solids reduction is. It's hard to tell. But on the high rate systems, the UASB, EGSB systems, you don't want the TSS and the influent to be more than the influent. So influent should equal effluent. And if we're lucky, the effluent will be a little less than the influent. The settleable solids, don't really know or care in the low rate systems, but on the high rate systems that depend on granular sludge, it's important that we don't lose those granules. So our rule of thumb is when we do a settleable solids Imhoff cone test, that we want to see less than 1 milliliter per liter of granules in 5 minutes of settling. That's really important. If you have more than that, you could be losing sludge. So you want to, which isn't a good thing. So less than 1 milliliter per liter of granules in 5 minutes is important. The macronutrients, we've discussed this. Again, can't emphasize enough. You need to have enough macronutrients to make sure that you get good sludge growth, which gives you then good system performance. COD to NTP ratio is about 1,000 to 5 to 1. On the reactor effluent, and this doesn't matter whether it's high rate, low rate, whatever. The ortho P in the reactor effluent should be at least 5 milligrams per liter, and the ammonia nitrogen should be at least 10 milligrams per liter. If you have those minimal residuals, you have enough nitrogen and phosphorus in the system to ensure really good system performance. Now I'm going to tell you the exception here. We have several plants where we have less than 10 milligrams per liter of ammonia nitrogen in the effluent, and I don't care. And I don't care because the system's working really well. I have 0 VFA in the effluent. I get good sludge growth in these plants, and I'm adding nitrogen. So at a rate that I know is at least the 1,000 to 5 to 1. So I know that it's going in there, and what I'm assuming is happening is that the nitrogen's all going to new sludge growth, which is okay, all right? And I don't care that I have less than 10 milligrams of ammonia nitrogen in the effluent, again, because in these particular cases, I have 0 VFA, I get good sludge growth and really good COD reduction. So I really don't care. So you have to be able to, what's the word? You have to be able to look at everything and make some judgments on whether that's good or bad. Okay. The micronutrients. You're going to test these a couple times a year. If you have less than the amounts shown in these charts, and the amounts are related to the influent COD, you want to make sure that you have a micronutrient cocktail that contains the elements that you're low on. So let's say that you're low on magnesium, copper, and aluminum. You want to make up a mixture that includes the magnesium, aluminum, and copper so that you meet these influent requirements. Okay. Okay, what's the biogas composition supposed to be like? 60 to 80% methane, 20 to 30% carbon dioxide, 1 to 4% water vapor, depending on where you take the sample, and 0 to 2% hydrogen sulfide. When you operate a plant, the amount of methane in the effluent and CO2 in the effluent is going to be a function of the influent COD concentration and the reactor pH. Those are the big ones. The higher the COD concentration, the lower the methane content in the biogas, and the higher the CO2 content is. And why is that? Well, that's because when you make biogas, typically 50% of it's methane, 50% of it's carbon dioxide. Methane doesn't dissolve in water very well, but carbon dioxide does. So if you have a very high COD concentration in your influent, you're making a lot of gas and a little bit of water. So you can't absorb as much CO2. So you're going to have a higher CO2 content in your biogas. Similarly, if the pH is high in the reactor, you're going to get a higher methane content. And that's because the higher the pH is, the more carbon dioxide that you can absorb in the water. That doesn't mean you're making less methane. And that's usually the important gas that's everybody's looking at, because that's what you're going to burn somehow and hopefully use. So you're not making less methane. It's just the ratio of the methane to carbon dioxide in the biogas changes. Now, normally when you're operating, you're going to run at a pretty constant methane CO2 ratio. So let's say you're making 75% methane and nearly 20% CO2. Okay, that's good. But if someday you come in and your pH and everything's the same, and you have now only 60% methane and 40% CO2, something's wrong, because now I have a lot more carbon dioxide in my wastewater, and that means something's not right, and I need to look at that adjustment. Something's out of whack, and you need to adjust something. The other important gas to look at is the hydrogen sulfide, because hydrogen sulfide also dissolves in wastewater, and H2S is toxic to the anaerobic bacteria. If you have an H2S concentration over 2%, you could be inhibiting the activity of your biomass. So you want to keep track of that. That doesn't mean the system won't work above 2% hydrogen sulfide, but you have to run at different conditions. You have to run at lower F to M ratios and maybe slightly higher CODs to make sure you get good biomass activity. Above 4%, you're going to run into real trouble. You could run into toxicity issues. But again, something that you're going to find out, and every plant's going to be different, what that normal concentration is. Okay? Calculations. COD and BOD reduction. What typically can we see COD and BOD reduction wise? In our high rate and in all systems, the soluble COD reduction should be between 80 and 90%. And it's going to vary depending on industry and wastewater characteristics. And the BOD reduction should be 90% or more. The total COD reduction depends on the suspended solids in the effluent, which is a function of the influent TSS and a lot of other things. Because you got to remember that the total COD is equal to the soluble COD plus some number X times the TSS. And that X is a function of the type of suspended solids that we're talking about. Now, there's exceptions to this. And one of them I see is in the yeast industry. Yeast production is a fermentation process where they mainly use molasses as the substrate to grow the yeast on. In that case, the COD to BOD ratio on the influent could be somewhere between 2 and 3. And that means that there's a lot of COD that's not degradable biologically. So you'll see a COD reduction of maybe 65%, but the BOD reduction will still be 95%. So again, it depends on the type of wastewater, but if a typical food and beverage industry type wastewater is what you have, you should be getting soluble COD reductions much greater than 80% and BOD reductions above 90%. Okay. One of the important things is how much sludge is in the digester, whether it's a CSTR or a UASB, EGSB high rate system. In our UASB, EGSB high rate systems, we determine the amount of sludge in the reactor by taking samples of the biomass at various levels in the reactor. Those levels represent a certain volume in the digester. At each sample, we do a TSS and VSS on that sample and integrate those measurements over the height or the volume, over the volume for each of those layers and add them up. And that's how we get the amount of sludge in the reactor. And a CSTR or lagoon type system is really just a mixed liquor suspended solids measurement of the mixture in the digesters, in the anaerobic reactors, CSTR or lagoons. And why is that important? Because remember, we're going to use this biomass number to calculate the F to M ratio, the food to mass ratio. And the more mass you have in there allows you to treat more food. So that's important. And let's go to the next slide. Food to mass ratio. Typically, in an anaerobic high rate system, the typical F to M ratio is 0.5 to 0.6 kilograms of COD per kilogram of VSS per day can be treated in a high rate system. So that's, again, we needed to know how much sludge we had in the reactor to calculate out that F to M ratio. In high rate systems, you can run at an F to M of 0.5 in some systems. That doesn't mean every reactor can, but I've seen reactors run for years at 1. But most of the time it's going to be 0.5 to 0.1. In lower rate systems, in the lagoons and in the CSTR type reactors, it's going to be lower than that. It's going to be 0.1, 0.2 usually, kilograms of COD per kilogram of VSS per day. Okay. Volumetric loading rates. Okay. In anaerobic digestion, the standard unit for describing the load to a system isn't pounds or kilograms of COD per day. It's kilograms of COD per cubic meter of digester volume per day. So it's all naturalized or to the size of the digester. So in a CSTR or a low rate lagoon system, the volumetric loading rate will be 1 to 5 kilograms of COD per cubic meter of digester volume per day. And that's sort of shown in that top picture where you have 1 star in that square box, which represents a given volume. In a UASB high rate system, you're going to have 8 to 15 kilograms of COD per cubic meter of digester volume per day. And look at the middle square there. You have 3 stars in that same volume. So you have more in a given volume. In the EGSB high rate systems, you're looking more at 15 to 25 kilograms of COD per cubic meter of digester volume per day. And that's represented in the third and bottom square there. And why is this important? If you're running along in a UASB system and you calculate that your volumetric loading rate was 25 on a day and your VFA was high, it's most likely telling you that that's why you're having trouble, because you fed it a lot more than the system was designed for. And that's why this number is important. And again, it doesn't depend, like one UASB system, and I guess I should say the reason we do these all related to the digester volume is because you can relate different reactors. So let's say I have a brewery with a 100 cubic meter reactor and another brewery with a 3,000 cubic meter reactor. If they both have a volumetric load of 15, it means the same thing. I don't have to know that the one with the 100 cubic meter digester treated, X pounds or kilograms per day. It's all related to that cubic meter of digester volume, and that's what's important. Okay. The methane yield, why do I care? We measure this because there's a standard amount. If you took a mole of sugar and broke it down into methane and CO2, just from the chemical breakdown, chemical equation, and the ideal gas law, you would know that you could theoretically make approximately 0.35 cubic meters of methane for every kilogram of COD that was reduced. Now that number could be lower if you get COD reduction without biogas production. And that's typically in anaerobic digesters caused by the reduction of sulfate to hydrogen sulfide. And for every kilogram of SO4 that's reduced, you reduce 0.67 kilograms of COD, but you don't make any methane. And why are we checking this? Because if we don't get that number, we know that something's wrong. So, okay. So this goes to the COD balance. So we want to watch that the incoming COD in kilograms per day and the outgoing COD from the reactor plus the COD that was reduced to the biogas should all equal out. So a kilogram of COD reduced should give us 0.35 normal cubic meters of methane. And that tells us really how good our measurements are and our analyses are. If the numbers don't match up, there could be an error in the testing or in the instrumentation. And either way, if something doesn't balance out, corrections need to be made because you need to know these numbers to make sure that the biomass is working well. Again, the bugs can't talk to you, so you're relying on all this testing that we just talked about and making sure that you have a good home for the bacteria to make sure that everything's working well. Okay? That's it. We're going to wrap up. Do we have time for questions?
Sure, Jill. Thanks so much for that presentation. Just to remind everyone, there is that question panel on your screen. If you have questions about today's presentation or any of the content Jill discussed, feel free to go ahead and enter that question in. Also, if you have some just general questions about your facility or your process, your wastewater process related to anaerobic digestion, go ahead and enter them in as well. Jill's a great resource and probably could answer most of your questions here. Just to get started, we do have a leading question. When you were talking about pH variances, you're saying to measure and compare the inline measurement with the lab measurement. Can you talk about what is sort of the threshold for where there's some cause concern between the two measurements, the inline versus the lab measurement?
Okay, very good question. I usually use 0.2 pH units as my standard. It might be a little more in the reactor effluent. It might be a little more give and take there because in the reactor effluent the reactor effluent sample is saturated with carbon dioxide when you take it out of the line. And when you take that out of the line, which is usually a pressurized line, you release carbon dioxide. And when you release carbon dioxide from the liquid, you increase the pH a bit. So your lab pH reading is likely going to be just because of that more than what's in line. So you might want to take a little more leeway with that. But I usually use like 0.2. If the difference between the lab and the inline reading is more than 0.2, I'll take out the probe. I will clean the probe and put it in a buffer 7. If it reads 7, it goes back in the line. If it doesn't read 7, I'll calibrate the pH probe then and then put it back in. I also recommend do not calibrate your inline probe with the pH that you get from the lab. Use a buffer, use that, and then put it back in the line. But don't try and make it. Don't try to make the lab and the inline probe match. It's never going to happen again because, especially because if there's any CO2 in the sample that you pulled out of the line, it's going to be higher than what's really in the line. Okay.
Another question we have here is when you talk about the volumetric loading rate, you said you're basing that calculation on the digester volume. Why wouldn't you make that calculation based on the sludge volume in that reactor?
Good question, and I don't have a good answer to be answered that because it's really an F to M question then. It's the sludge volume really doesn't, it's not the sludge volume that matters, it's the sludge kilograms that matter, and that's really what your F to M is. I hope that answers the question. I mean, I have to say in a high rate system, the volume to some extent does matter because in a number of cases, you need a minimum depth of sludge to get good performance, but that varies from plant to plant. So some plants may need 10 feet of sludge in a UASB, others may need only 6 feet. And that's really wastewater dependent. So I really don't have a good, it has to be at least 5.365 feet to make sure that you have a good sludge bed in there and a good, volume of sludge. And same thing for EGSBs, it would just be a different depth. Each plant's different, and what that minimum is to get a good COD reduction and a good system performance.
Okay. And another question we have came in: how do we increase the methane production in biogas per COD reduced? And similarly, how do we measure this more accurately?
Okay, you can't. You can't make more. You can't physically make more. Again, if you just write, I'm sorry, can't write it down for you, but if you take C6H12O6, which is sugar, and you do it and go equal CO2 plus CH4, you physically can't make more methane. Okay, so for every kilogram of sugar that you reduce, you can only make so much methane. You physically, chemically can't do more than that. And the bacteria are just doing that chemical conversion for you. So you physically can't make more than 0.35 cubic meters of methane per kilogram of COD reduced. Okay, and that's like an approximate number because it takes into account that you're really not at standard temperature and pressure and yada chemical wise, but you physically can't do more than that. And what was the second part of that question, TJ?
It says, how do we measure this more accurately?
Okay, so to measure it accurately, you need a very good gas meter that is working well. I have trouble with gas meters. I don't know sometimes they work really well, sometimes they don't work so well. And I don't know why, because I'll see the same type of gas meter work well in one installation, but not in another. And I don't get it, but you need a good gas measurement. And you also need to know not the total gas flow, but you also need to know the quality of the gas. So you need to be able to measure the methane content of the gas. And typically, like I told you, the Endress-Hauser now has, not that I'm a Endress-Hauser salesperson, but I know that we've used a meter that I really like, that the gas flow reading has been very good, and the gas quality reading has been good, and we do get 0.35 cubic meters of methane per kilogram of COD reduced. If you don't have a way to, if you're not measuring one of these Endress-Hauser meters, you have to measure typically the amount of CO2 and the amount of H2S in the biogas and back calculate the amount of methane that you would get. So the amount of methane in a gas sample would be 100% gas minus, let's say, 3 to 4% water vapor minus the percentage of CO2 that you measure in the gas minus the amount of H2S in the gas. And that'll give you a good measurement of the percentage of methane that's in the biogas. And again, that you get that tells you how much, using your total gas flow and the percent methane, what your methane production was, and compare that to your COD reduction, and you should get that 0.35. So that's what you need to get good measurements.
All right. Thanks for those tips, Joe.
Okay. So also it's tough to get these. Usually we use Draeger tubes or Gas Tech tubes or REA tubes to measure that CO2 and H2S quality, by the way. Okay. Sorry, TJ.
No, we have time for just one more question. We're just about out of time, but it says my COD reduction is 95%. VFA is less than 1.0, but sludge growth is net zero. What factors could be suppressing the biomass growth? Do you have any ideas, Jill?
I bet you do have biomass growth, but I'm guessing that it's washing out. Okay, so I'm guessing that your effluent TSS is higher than your influent TSS, and I'm guessing that the sludge that you are growing is just washing out.
Great. Okay, and that's it for our questions. That's it sort of for our time. Just want to remind everyone, you'll be offered a survey at the end of the seminar. Go ahead and please take that survey and help us improve these webinars in the future. And also, if you could just let us know if there's someone in the room watching the webinar with you that we need to provide a certificate with, we want to make sure that we do that as well. We really want to thank Jill for all of her many decades of expertise in anaerobic digestion and bringing that to us in this webinar platform. It's invaluable. And also want to thank everyone who spent an hour or so of their day taking the time to learn a little bit more how they could operate their systems better. Again, we're here. If you need anything, feel free to reach out to us. Send me an email, send Jill an email, and reach out to your contact at Veolia, and we'd love to make sure that we support you the best that we possibly can. So that concludes our webinar, and I wish everyone to have a great day. Thank you.
Thanks, guys. Thanks, everyone.